Okay, we are very happy to have Mallesh Pai from Rice University talking about the strange case of privacy in equilibrium models.
Thank you, everyone. I'm the last person holding you up between now and wine, so I'll try and keep this short and painless. A note on my co-authors, Katrina, whose name is misspelled, is here, so she's going to handle the hard questions. Aaron and Katrina have been responsible for teaching me about privacy. I should also mention that the third co-author, Rachel, is a student, Katrina's student, who's on the job market this year, and she's extremely well trained both in privacy and in both in the computer science side of privacy and in the economic side of privacy, and more broadly in computer science and economics. So if you're sort of at an institution that's looking to hire a top quality candidate, I'd strongly recommend her. Okay, oh, and I have, since I'm not one of her advisors, I can say this with absolutely no bias. So, since it's been a long day, I thought I'd start with a comic, and there's, privacy means lots of things to lots of people. Here's sort of everything that could go wrong in privacy in one comic. So this is something about going to a Google store. The guy at the Google store says, hello, Robert Howard Smith and his wife with the Wi-Fi network known as Smith's D-Link. We hope you enjoyed your journey from here, guided in part by Google Maps. We already know what you will most likely purchase. Here it is. You've been charged the maximum we think you'll pay for it, and we've posted a complimentary blurb about your purchase on your G+ accounts. Thank you for shopping Google. We predict you'll be back next week. If you need a drive home, one of our self-riding cars is available. And the couple walks out, one saying what happened, and the other saying, I really wished I'd pushed the I'm feeling lucky button. So, I mean, it sort of illustrates there's a whole bunch of things going on, lots of aspects of privacy that we've touched upon, especially in Alessandro's overview today. I'm going to try and narrow the scope a little bit to a scope that's been focused on in a couple of talks, and that's sort of this idea of privacy and statistical analysis. I'm going to settle for a very limited desideratum, that is, that we want to analyze a data set. This data set is comprised of possibly sensitive data of a bunch of individuals, and what we'd like is that whatever we reveal from this analysis doesn't reveal very much about any specific individual in the data set. Now, I had one more slide that was going to set this up a little better, which was the notion of what I meant by reveals very little. The notion of differential privacy. Luckily, Katrina already explained that, and she taught me, so there's no point for me to tell you about it again. So I'm going to jump over to the next slide. From my point of view, here's my sort of, as an economist who doesn't physically pick up or try to program differentially private algorithms, here's my point of view. The differential privacy definition is a nice definition for us to work with as scientists, because it balances two things. One, it does provide a hard mathematical guarantee, that is, that if the notion of privacy that you're interested in is privacy in statistical analysis, then you're sure that a good implementation of a differentially private algorithm will never reveal much about any individual. However, it also does one other thing which is kind of important for a definition. It allows us to gainfully earn a living, which is that that's non-trivial possibility. Over the past decade, there's a large body of computationally tractable algorithms that let us do differentially private versions of the various tasks that we set out, popular statistical tasks that we want to do. And the state of the art in the literature is that this is almost a turnkey solution. All you want to do, if you want to do something statistically but you're worried about privacy, go rifling through, find a differentially private version. Now, I say from a library, I wish I meant that it's already been coded up. Chances are it's not been coded up, but chances are somebody really smart, probably Aaron or Katrina, have already figured out how exactly to do it. They've written and published an algorithm in a conference somewhere. And all you have to do is get a smart coder to code it up, and you're good to go. The part that doesn't get stressed, or doesn't get stressed often enough, except in Ian's talk earlier today, is the second question. The notion of differential privacy comes with a parameter, this epsilon. How much loss of privacy are you willing to tolerate? And it's this choice of epsilon that I'm going to go even further than Ian's talk, or try and go in a different direction than Ian's talk in trying to elucidate. So if I had to summarize Ian's talk in one slide, I mean, this is almost a caricature, but it's basically that what you're trying to do is you're trying to trade off two things when you choose epsilon. You're trying to trade off the claim of the analyst to conduct accurate analysis. That is, if all you cared about was the claim of the analysis, then you might as well set epsilon to infinity or epsilon really large. And then you'll get an accurate analysis from the existing statistical algorithm, but of course there might be a large privacy loss. Conversely, you might care broadly about the claim of the individuals to preserve privacy. And only, so if you really, really cared only about privacy, then only pure noise will satisfy epsilon equals 0. The way sort of I think of Ian's talk is that we're trying to balance these two things. We're trying to balance the claim of the analyst with the claim of the individual. Our question is, so then it just becomes an exercise in estimating one, estimating the other, and equating the two. Our question is, does this intuition actually accurately always represent the basic trade-off when it comes to choosing a privacy policy? Parenthetically, for the purposes of this paper or my talk, the grandiose word privacy policy just represents mathematically the level of epsilon you're plugging into your differentially private algorithm. So when I say privacy policy, all I mean is pick the number for your algorithm. The basic point of this paper or talk is we're not trying to pick, if anything, we're trying to build on sort of work like Ian's. That is, if you're talking about data sets about immutable characteristics, or agents' choices are non-strategic or unresponsive to the privacy policy, or the data was already collected and all done long before anyone foresaw a privacy problem, then go look at their work, or go look at other work that tries to do this. The point we're trying to make here is that this intuition may be very badly misleading if these properties are not satisfied. So what kind of settings am I thinking about? I'm thinking about settings where a privacy policy is announced or foreseen by individuals. They understand that a choice they subsequently make will be recorded in a data set and analyzed subject to that privacy policy. So it's not like it's my height and I can't change my height regardless of what the privacy policy is. And it's not like I don't care about the privacy policy at the time I make my choice. I understand the privacy that I'm being subjected to at the time I'm making a choice. And that the outcome of the analysis that will be conducted privately is utility consequential to the agents. That is, they also care about the outcome of the analysis when they make that choice. So the point we're trying to make is, if these three conditions satisfy, and I'll try to convince you that a lot of sort of, if you think about internet repeated sales or things like that, then these conditions may well be satisfied. Then the intuition of we're sort of trading off these two claims in a linear fashion, that intuition may not be satisfied and may be badly misleading. To try and bring this point home, I'm going to construct an illustrative model. My paper is going to be this paper is going to be purely theoretical. And this illustrative model is not a model that I claim perfectly captures a realistic setting. It's just a model that we think does the best possible job of cleanly demonstrating a phenomenon that is endemic to a whole bunch of models with these strategic choices. Okay? So our illustrative model is going to be a model that exists across two periods. And in these two periods, a consumer will sequentially interact. In period 1, the consumer will interact with the seller. During that interaction with the seller, the consumer privately knows her valuation for the product. So she knows how much she's willing to pay for the seller's product. The seller is going to set a price for this product. The seller only cares about the seller's revenue. And the only thing that's revealed about this transaction is a noisy purchase decision. So whether or not the consumer purchased or not is not privately revealed, is not publicly revealed. Instead, some noisy version of that. Sometimes if the consumer bought, it still appears to the outside as if the consumer didn't buy. Conversely, sometimes if the consumer buys, it still may appear to the outside that the consumer, if the consumer didn't buy, it still may appear to the outside as if the consumer bought. That's the only information about the transaction that leaks to the outside. Yeah.
So you look at the binary decision.
Yes. So I'm going to look very much at a binary decision case. And again, it's not, I'm not making, I want to stress that the reason I made this choice is I want the math that will follow to be as simple as possible, to try to make the basic forces as clear as I can. It's not that these effects will go away if we move to a model where there was a more rich decision that the consumer made. It's just that the math would be more complicated. Okay. Now, this purchase decision will be relevant, or this observed purchase decision in our model will be relevant for period 2. In period 2, an advertiser will have to choose whether to show one of two ads for a consumer, to a consumer. Think about one ad as being sort of, you advertise a good low fee, low interest rate credit card, and the other ad is sort of advertise a high interest rate credit card. The ad the advertiser would like to show depends on the consumer's, on a type of the consumer, and that type is correlated with the consumer's valuation. So in some sense, the consumer's purchase decision reveals some information to the advertiser that the advertiser would like to use for targeting. Okay? The trouble is that the consumer would like always to be shown the same ad. So all consumers want to see the low interest rate ad. It's just that the advertiser would like to show the low interest rate credit card ad to the consumers it thinks are creditworthy, and the consumers and show the high interest rate credit card ad to the consumers it thinks are not creditworthy. By strategizing on its purchase decision in period 1, the consumer can try to get the better ad or the better offer in period 2, and these sort of incentives across these two models are going across these two periods are going to link the actions of the consumer and therefore cause potentially strange stuff to happen when you change the privacy. That is, you change the noise in the purchase decision of the consumer that will be in the purchase decision of the consumers, you change the noise in the observed purchase decision of the consumer, that is what the advertiser gets to observe. This is going to be linked via equilibrium through a very simple mechanism. When you change the privacy policy, you change the advertiser's beliefs and therefore the ad shown as a function of the observed purchase decision. So when you change the privacy policy, there's a little more noise. The advertiser might want to show a different ad for the same observed purchase decision. Since the consumer cares also about the ad she sees, on the margin, this may change her purchase decision. As the demand changes, because the purchase decision is changing on the margin, from the perspective of the seller, the demand curve that the seller is seeing has also changed, and therefore the optimal price that the seller charges has further changed as a function of the advertiser's beliefs. All these three things have to be jointly determined. So you'll have a nonlinear system of equations that jointly determine the advertiser's beliefs, the consumer's demand function, and the seller's optimal price. And these nonlinearities, because of these nonlinearities, your comparative statics may be wonky. That's the basic sort of point we're pushing in this paper. Unless there are any further questions, I'll proceed. All right, so broadly, our main point is things may be exactly wrong in the old intuition that we had. That is, everything can be exactly the opposite of what you think. If you change epsilon, that is, if you switch to a privacy policy that is even more private, so you make epsilon lower, the new equilibrium, the new noisy purchase decision in equilibrium may have more information about the consumer's type. Mutual information between the consumer's type and the purchase decision may actually increase even though you're adding more noise. The advertiser's net utility may increase with higher privacy because he's getting more information. And conversely, the consumer's net utility may decrease with higher privacy. I use the words may in all these settings because obviously it's going to depend on parameter values whether this sort of thing occurs or not. Our main objective is to point out that these things can happen and they can happen in reasonable models. And what I'm trying to do, therefore, is just point out the mechanics through which this, the mechanism through which this occurs, so that we can try and model it further in specific settings if we are focused on thinking carefully about privacy policy. Yeah.
Well, I'm terribly sorry, maybe I missed something, but are you talking about static models or dynamic models?
So I'm talking about I'm talking about comparative statics. So it's a dynamic model, but I'm comparing two things. I think of, let's say, epsilon 0.05. What's the equilibrium under epsilon 0.05 versus epsilon is 0.04. What's the equilibrium under epsilon 0.04? Now, epsilon 0.04 has a lower is a lower epsilon level, therefore more privacy.
But you're so you're looking at the dynamics models, but only at equilibrium then?
Only at equilibrium, yes. So this is this is what we in the economics literature, it's what we call comparative statics. That is, we compare the equilibria across different parameter values, but we don't look formally at any re-equilibration process. We just.
But then you make an assumption that there is in fact only one equilibrium, yeah?
I'll talk about multiplicity of equilibria as well.
Can you maybe give some preview of the intuition of why the first thing can happen? Is it like more separated?
I mean, it's.
They will be more asymmetric in the equilibrium.
I mean, essentially the idea is going. When you go through this basic mechanism, right?
Okay.
If you look at what is it, point 2, the consumer cares about the ad she sees, so this may change her purchase decision on the margin. Essentially, I'm going to construct a model where the purchase decision changes faster than the noise that you're adding. So there's more information being added in by the purchase decision than the noise you're taking, than the information you're taking out by adding more noise, if that makes sense. Yes.
I think I missed something, which is why does the consumer care about the privacy policy other than through its effects on the advertiser?
It does not. The consumer does not. I'm going to have a formal model in a slide. I've already taken longer than they'd let me get away with that pen, but I'm at Rice now, so it doesn't matter. The consumer. This is what. Alessandro termed, privacy as an intermediary good, not as a final good. Here, I don't care about, the consumer doesn't care about privacy per se, but the consumer does care about the ad he gets to see and fully understands and forecasts correctly the ads that he gets to see as a function of his purchase decision. Okay?
Yeah. So I guess I'm having trouble with the intuition then for why, if you increase my privacy, then I'm going to be more likely to buy the good that gets the, but I guess we'll see.
I mean, I'll show you in a minute. All right, good. So, bunch of related work. Luckily, almost everyone who's contributed to this was either in the audience or on Skype, so ask them. But there's a lot of cool work, and what we're trying to do is just push it further in understanding sort of even more possible issues with selecting a privacy policy. There is some of the tractability in these models will possibly come, instead of trying to work with dynamic games, will possibly come with trying to use mechanism design. And I just wanted to advertise two other works that haven't been cited as much, one by Calzolari and Pavan, on sequential sales and privacy, and the other by Bergman, Brooks, and Morris on the limits of price discrimination. So I think there's a lot of scope for using mechanism design and math programming rather than games, which inherently are fixed points and therefore funny objects to try and work with. But that's all I'll say here. So luckily there's a nice collection of work on this. I'm going to give you two models, and I really mean when I say a model for theorems. So I'm going to give you a model, the simplest possible model I could write down, where we could prove theorems about the possibility of these inversions happening. And then, because theorems at 4 in the evening can be a little abstract, I'll show you some pictures by generalizing to what I'll call a model for pictures. Okay? Here's the model. In period 1, the consumer privately knows her value for the good, and it takes only one of 3 possible values. V1 is the high value, V3 is the low value, and V2 is some value in the middle. The seller posts a price P, consumer chooses whether or not to purchase, and once the consumer chooses whether or not to purchase, neither the seller's price nor the consumer's purchase decision are directly revealed. Only the consumer's purchase decision, which has been flipped with probability 1 minus, flipped with probability 1 minus Q, is publicly revealed. So with probability Q, your purchase decision is directly revealed to the advertiser, but with probability 1 minus Q, it's flipped. If you bought, it says the advertiser is told you didn't buy. If you didn't buy, the advertiser is told you bought. If you, again, the modeling assumption here of symmetry is just to make our lives easy. We already know reasons for which you could have a flip in one direction or the other. If you and I share computers, then maybe you bought the product, but when I show up, the advertiser thinks I bought the product. Conversely, if there's a right to be forgotten, which the EU believes in, then even though I might purchase the product, you might have forgotten about it by now. So both directions are possible. We've just combined them symmetrically in this model. In period 2, the consumer has either a type T1 or a type T2, and the main sort of twist is that it's correlated with your period 1 type, but not perfectly. So V1, if you had the high value in period 1, you definitely have the high value, you have type T1 in period 2. If you had the low value in period 1, you definitely have type T2. It's just that the middle value might have type T1 or type T2. The advertiser wants to match ad and type. So she wants to show ad A to type T1, ad B to type T2. The consumer wants to see ad A regardless. Going back to my example about purchases and credit cards, think of the purchase as being some purchase that signals wealth. High value types are probably wealthy, and therefore you also want to show them ads for, you want to show them the fancy credit card, the low interest rate credit card because they're credit worthy. Conversely, low types are poor. You want to give them the high interest rate credit card because you're not sure they'll return your money. And you're not sure about the middle type. Your beliefs are, there you need other information that you couldn't glean fully from the type. Okay? The consumer always wants to see the low interest rate credit card. The only connection between period 1 and period 2, the privacy policy, is that I have some additional utility that I get from seeing the high interest rate credit card offer, the low interest rate credit card offer in period 2, and I'm willing to maybe make a suboptimal purchase decision to make that happen. Okay? I just want to, we were very happy when we hit upon this model because we could finally solve it completely, but I don't want you to be wedded to this model. I just want you to sort of understand that this model is evocative of a whole collection of scenarios where there's some linkage between a choice you're making in period 1 and some future outcome. And if that future outcome is utility consequential, then weird things can happen in equilibrium when you change the privacy policy. That's our broader takeaway. Okay. First, advertiser is Bayesian, understands all these probabilities. I'm not going to introduce, I'll try and keep the amount of notation I introduced to a minimum. It is 4:30 now. So one thing is obviously there's some threshold cutoff, right? If I believe that that threshold depends on all the parameters that I've written down, let's not worry about them, but there's some threshold. If the probability with which you believe that the agent is type T1 is high enough, then you want to show him add A, because you definitely want to show T1 add A and T2 add B. So at some threshold you'll start giving add A, and some threshold you'll start giving add, below that threshold you'll show add B. The second thing comes from the nature of the correlation. Type V1 always, value V1 always has type T1. Value V3, the low value type, always has type T2. So in some sense, because consumers face a posted price in the first period, whenever you see that the consumer bought the good, that's good news about the consumer's value. And because it's good news about the consumer's value, it must also be good news about the consumer's type. That is, the advertiser's posterior probability about the agent being of type T1 is higher when she sees the consumer purchased. This is just the nature of Bayesian updating. And the single crossing assumption, the assumptions made on the correlation structure. So I've combined so that's sort of two high-level observations from this model. And because of these two high-level observations from this model, in equilibrium, only one of three things can be happening. Depending on what's happening in other parts of the game and various parameters, there can be only three kinds of advertising equilibria. Two advertising equilibria are basically if you're really sure, regardless of what the agent is doing, or really sure that is very high, your posterior is too high regardless of whether he bought the good or not, or too low regardless of whether he bought the good or not, then you'll just show the same ad in period 2 regardless of the observed purchase decision. We call these the uniform advertising. Because your probability, the posterior you place on the agent when he purchased is higher than the posterior you place when he didn't purchase, the only discriminatory advertising equilibrium potentially is that if you see that the agent purchased the good, then you show ad A, and otherwise you show ad B. You couldn't possibly have an equilibrium where the converse happened. This third is going to be our main is going to be the main thing that drives the interesting results, that is this discriminatory advertising. But let's continue down this road a little bit. So it's either 1, 2, or 3. As far as the consumer is concerned, his purchase decision, he doesn't have anything to do in period 2. He just gets to show up and see an ad. So all the consumer does is has to choose whether to purchase the good or not in period 1 as a function of his value and the observed price. As a function of his value and the observed price in period 1, the only other thing that matters to this consumer is his forecast of the advertising strategy that the advertiser is following. If he thinks that the consumer, if the consumer thinks that the advertiser is either uniformly advertising A regardless or uniformly advertising B regardless, then the consumer doesn't care about the future, right? He can't affect the future, therefore he doesn't take it into account. It's as if he purchases myopically, that is, purchases if and only if her value exceeds the price. The price the seller charges then therefore depends only on the distribution of buyer values, and intuitively, if the purchase decision is noisy enough, then then there has to be a uniform advertising equilibrium. If it's noisy enough, then it's almost as if the purchase decision is not revealed. Because it's almost as if the purchase decision is not revealed. The consumer is purchasing myopically based on what will happen, based on only the price today, and therefore by continuity there's some sort of interval around half. That is, there's some highest level Q bar such that whenever the purchase decision is flipped, transmitted only with probability half to Q bar, that is, there's a lot of noise introduced, and there's a uniform advertising equilibrium Whether it is a uniform advertising equilibrium with ad A or ad B depends only on which is the uniform equilibrium when no purchase decision is revealed, or alternately the purchase decision that is revealed is pure noise. So this is just straight up, this is the easy part. Let's think about the discriminatory advertising equilibrium. The discriminatory advertising equilibrium is going to be slightly more interesting, and hopefully at this point this will answer Ian's question from earlier. In the discriminatory advertising equilibrium, both types, remember, both types of the consumer prefer to see ad A over ad B. They prefer it to the tune of delta. Therefore, in a discriminatory advertising equilibrium, a consumer may choose to purchase the good in the first period, even at a loss in terms of his first period valuation versus the price being charged, in order to improve his chance of seeing ad A. Given the privacy parameter Q, purchasing provides an expected probability gain of seeing ad A of 2Q minus 1, given you purchased versus didn't purchase. So the total expected gain in utility is 2Q minus 1 plus delta. 2Q minus 1 times delta. Now note that if I believed that therefore the effective utilities of the three types of agents from purchasing are either V1 plus 2Q minus 1 delta, V2 plus 2Q minus 1 delta, or V3 plus 2Q minus 1 delta. All three types of agents have that thing dumped in, but the optimal price can't be the lowest price, because at the lowest price everybody would be purchasing, and that would violate, if everyone was purchasing, you couldn't have a discriminatory equilibrium. You don't learn any, you know as an advertiser that you're not learning anything from the signal that you're seeing. Okay? Now, if on the other hand, so that leaves two possible prices, and such equilibria occur for high levels of Q. One source of the pathological behavior is going back to equilibrium multiplicity, which I'll show more in terms of pictures in a few minutes. But one possible source of pathological behavior is due to the equilibrium multiplicity. So for instance, if we have a uniform equilibrium from half to Q upper bar, and potentially a discriminatory equilibrium from Q lower bar to 1, then a small increase in Q across Q upper bar or decrease in Q across Q lower bar necessarily changes the kind of equilibrium being played. So if you believe in equilibrium multiplicity, then there's that sort of mechanical source of pathological behavior. But there's one more important source of equilibrium of pathological behavior, and that's the one I want to focus on in this talk, which is, remember, the price is either V1 plus 2Q minus 1 delta or V2 plus 2Q minus 1 delta. This is the optimal price that the seller charges as a function of Q. As Q increases, at some point it is possible that the optimal price jumps downward from V1 to V2. Okay? Previously, if I may use a little bit of chalk, previously I was choosing in the myopic case, for instance, or the case where there's a lot of noise, I as the seller am choosing between V1 times the probability you buy if I price at V1 and V2 times the probability I buy at 1 minus FV2. If V1 and V2 are close enough, then it could be the case that this is happening here but this is happening here. So as you increase Q, the right hand side is increasing faster than the left hand side by observation, because 1 minus FV2 must be larger than 1 minus FV1, and at some point suddenly the seller finds it in his advantage to drop the price. When the seller finds it in his advantage to drop the price, remember V1 always had a type of T1. V2 is noisy. So you're decreasing the noise, you're decreasing the noise, you're decreasing the noise, and you're getting less and less noise. Then at some point suddenly the seller drops the price discontinuously. When the seller drops the price, a ton of more noise enters the system because these V2 buyers are now buying as well. And that's exactly sort of the simple source of this additional noise that's entering the system. I hope that makes sense. This is sort of a generic phenomenon. So as long as that price drop can occur, you'll also get the corresponding equilibrium non-monotonicity. This just goes over in words what I talked about on that slide. Good. All right, time for some pictures. So to show you some pictures, and I like these pictures because they carefully illustrate the same mechanism that I was saying before, but in the context of a slightly richer model. Let's suppose that the buyer's value is now uniform on 0, 1, and that the probability is still correlated. That is, the probability that a buyer of value V has type T1 is given by V. So buyer of value 1 is definitely type T1, buyer of value 0 is definitely type T2, and anyone in between is kind of mixed up. Okay? More generally, our results will go through for this set of standardish assumptions from mechanism design, but you can look at the sort of typed up paper for that. Here's sort of a useful beginning. As when you're suffering and when you're thinking about equilibrium with a possible discriminatory since the buyer's value is distributed uniform 0, 1, if we are in a uniform equilibrium, then as a function of Q, if we're in a uniform equilibrium, the price that the seller charged doesn't change. That is, it stays constant at 0.5. On the other hand, if we're in a discriminatory equilibrium, as Q increases, that is, as there's less and less noise in the system, the probability of you flipping goes down, buyers are willing to pay more and more in order to purchase the good, so that they seem like the good type to get the good ad. So as that starts happening, the sort of price that the seller charges goes up, and the lowest value that purchases goes down. So there's this divergence, this wedge, and that wedge is exactly the expected gain in the probability of seeing the ads as there's less and less noise. So the blue line and the red dotted line are respectively the monopolist's price and the cutoff in period 1. As a function, now because the cutoff value and the price being charged, because they're changing, the corresponding posterior of the advertiser upon seeing a noisy purchase decision is also changing. And they're demonstrated exactly again by the corresponding lines. So the black line is now the sharply declining line, because I know that it's exactly buyer 0.5 buying and buyer below 0.5 not buying, and that stays constant. I know further that I further know the probability, the posterior belief that I have that the agent is of a particular type as a function of the observed purchase decision. And by crossing it with, we now have sort of two possible cutoff values. So suppose the lowest, just for demonstration, we pick two cutoff values, 0.45 and 0.55. These were the thresholds that the advertiser needed in order to show ad A. You can see that there are potentially multiple equilibria, and you can essentially, from these posteriors and from where they cross, you can see which kind of equilibrium exists or which kinds of equilibrium exist at each Q. Okay. Finally, this is a plot of the mutual information between the observed purchase decision and the consumer's type in a discriminatory equilibrium. So the mutual information, I mean, it's just the smooth version of the phenomenon I was talking about before. And when I was talking about it in the discrete model, there'd just be one sudden downward jump in the discriminatory equilibrium because suddenly a lot more noisy people were coming in. Here, on the other hand, because the cutoff is smoothly falling, even though you're adding less noise, sometimes the number of people who are coming in who are of low value and therefore are very low probability to be type T1 are introducing a lot more noise into the purchase decision. So even though you're getting less noise, you might also be getting less mutual information. This kind of peaks out in this or bottoms out in this concocted model where we've picked the numbers to make it as stark as possible. The numbers were chosen in a way so that at no noise, you care so much about the ad that you will purchase regardless of what your value is. The firm knows this, so the firm charges the highest possible value but still gets everyone to buy. On the other hand, because everyone is purchasing, there is no information contained in the bit, contained in whether you purchased or not, even though you're seeing whether or not the consumer actually purchased perfectly. That's the main point of this enterprise. Similarly, the advertiser utility can be non-monotone. The non-monotonicity sort of peaks at a different point, but that's because the advertiser doesn't directly care about the mutual information. It cares about its expected value. So there's a mathematical difference between mutual information and what it actually cares about. And sort of that's all that's sort of the point I was trying to make, which is in non-strategic settings, like we saw, setting privacy policy is a simple balancing act. There's still a ton of work to do to figure out how to balance it, but conceptually, as an economist, it's a cost benefit trade-off, which at least in concept we know how to do, even if the actual measurement and so on is very difficult for a real world setting. The claim you're making is if it's a strategic setting, so if you're thinking about privacy policy for things like internet purchases, for things like Google or things like that, the changes in privacy policy can have non-obvious impact. And the lessons from information economics about counterintuitive comparative statics that we've been learning about since the 80s, all those results apply here. What I tried to show you was the simplest possible model, but I believe the insights carry over to all sorts of related fields. And finally, there's a bunch of modern developments in information economics, such as Bayesian persuasion and its applications, like Brooks, Bergman, and Morris, Bergman, Brooks, and Morris, that may provide helpful analytical tools to help us think through these questions. So that's all I got.
Thank you for finishing a bit early, so we have time for questions. Yes, please.
Well, from what I understood, so you have Q fixed, yeah? So
Yeah.
the probability of fixed. And did you look at the settings when it may change over time? So if this leads, if this kind of have an implication to which equilibrium it goes?
So, I mean,
I'm thinking, if you have like a public computer and for instance you have all the time people doing purchases there,
yeah.
so then it would be just getting biased, more biased in one way. So
I see. So we're not ruling out those. I mean, our model doesn't encompass those settings, and there are one of the papers I cited way back. Let's see if it's on there, and I actually cited it. Yeah. So Konitzer, Taylor, and Wagman look at a very specific case of essentially of one directional thing. So I think it's the opposite direction to what you wanted, which is I have a cookie, but sometimes I can make the cookie disappear. So I can pay a cost and wipe my computer clean. And they look at the equilibrium there. Our point wasn't to sort of think about all possible ways Q could evolve. We just wanted to say that Q has impacts that maybe we haven't fully forecasted yet.
And another question about types. So this also assumed to be fixed if
Yes.
you want to learn it.
Yes.
Also, in the example of public computer, you would get some sort of aggregate of people who were visiting there. Yeah?
That's, yeah, I think these are all interesting questions. I mean, in some sense, what I'm trying to say is, I think there's a great scope for modeling these questions and trying to understand, because once we model them, we can then start thinking seriously about what privacy policy achieves. But we haven't scratched that surface yet.
So can you go back to the sort of advertiser utility slide at the end?
Sorry.
So when you're on the right side and there's little noise, the graph, sorry.
Excuse me.
Yeah, so does the advertiser always show ad, or does the advertiser show the advert based on like a probability?
No, the advertiser
Always showing A when the price is low, it will always show A. Or something.
well, essentially the issue is, look, when the price is, when there's pure noise,
Yes.
it turns out that the advertiser is, numbers were constructed so that the advertiser is completely indifferent.
Yes.
And therefore, and because the advertiser is completely indifferent, it gets a pay. This model was constructed under the assumption that the advertiser gets 1 if he matches the agent's type, and 0 if he doesn't.
Okay.
And the two types are 50-50 in the population. So if you're not seeing any information at all, regardless of what ad you show, you're not going to match the consumer's type.
Right.
Right? So you'll match with 50% probability.
Yeah, so they're randomized.
So that's why that's 50-50. It doesn't matter whether he randomizes or he shows everyone ad A. He achieves 50% either way because it's 50% in the population.
Oh, yes, sorry, it's 50 on the left
Yeah.
side.
So
Yeah, okay.
and the same thing at the other end. At the other end, everybody is purchasing the good. So even though you're seeing that purchase decision perfectly, there's still only you still have no information contained in the fact that.
So when they have no information, they're showing a random ad to the user?
You can think of when they have no information, these numbers were constructed so that they're exactly indifferent between showing a random ad or either ad. They're all going to achieve the same.
My next question
Yes.
is then, do you model the consumer anticipating being shown the random one or showing like always A, the one they want, when the noise gets high?
Good question. So in this case, we are assuming because the consumer is exactly indifferent,
Yes.
we're assuming that, because the advertiser is exactly indifferent, we're assuming that if you purchase, you will be shown ad A, and if you don't purchase, you will be shown ad B. But because these beliefs, this is still consistent with equilibrium because there's no information.
Yeah. But if the advertiser were to randomize when they had no information, then consumer behavior would be different, right?
It would work out. Yeah. So, I mean, there are a ton of, one of the reasons I switched to the model with theorems rather than the model with pictures is because there are a ton of equilibria in this model that you have to work through.
I mean, because the reason I was asking, because if you assume like a sort of negative utility from showing ad A to people who are below the sort of threshold that you would desire, right? So if you're showing A to everyone, but actually for a portion of those, you're giving like a good credit card or whatever to people who with bad credit or something, then you would expect maybe to randomize to try and minimize that loss.
That's possible, but that would change the threshold. So you'd have to take that into account on your threshold on the posterior. So, but that's, interesting.
So this is because it's 4 now, going on 5 in the afternoon, so I think I may have missed this, but how are the advertisers' problem and the first period sellers' problem linked?
So it's a matter of how, they're linked through the correlation between the advertiser, they're linked through the correlation between the first period valuation and the second period type.
So the advertiser is not paying a price.
The advertiser is not paying a price.
Okay. So what happens if you make the advertiser and the seller the same? So non-maximizing the sum of profits across the two states.
That, I mean, but then I don't know how I should think about privacy. I'm the seller, but I already forgot whether you purchased or not. I mean,
Okay, well then charge
Sure, but-
charge a price. Right?
sure. So from other, I don't. So the paper I cited over here, Calzolari Pavan, think precisely of a world in which the first period seller thinks both about sort of contracts, sells you a good, but also charges Katrina some money to see what deal you signed with me, and works out the optimal thing for the first period seller, and finds that privacy is actually a good thing for the seller and a bad thing for the consumer. Okay, and that sort of theme. So they do it in a mechanism design setting, but this theme, Alessandro touched upon it. He has a paper on similar themes. Curtis Taylor had an early paper on similar themes as well. So this sort of sequential sale model is popular because we can get our teeth into it.
Okay. But you think this sort of counterintuitive comparative static, it all makes sense once I understand that everybody has an incentive to present themselves as a type 1 person. Right, ideally, I want to, basically I'm getting a pot of gold or something for a second stage.
Right.
Right, if I appear to be a
Good type,
person with some probability.
So I think these issues won't go away if you pick a different model. Again, similar issues have been observed. Similar sort of, the nature of the correlation changes the nature of the pathology, but you'll still find pathologies. You just have to, work out when they occur. So I'm not, these are all toy models anyway in my context, so I don't want to try and work out a complete compendium of what could happen, but it's like there's enough papers here that have done similar things that I'm sort of confident, and there's the larger literature on information economics so I'm sort of confident that weird things always happen when you change information structures. If you had to take all of 80s information economics and summarize it in one slide, it's that weird stuff can happen, right? So, all right.
Any more questions?
Time for a drink.
Yes. Thanks so much.
Thank you.